is being recorded.
Get started. Hey, good afternoon, everybody. Today's talk is about the multi-layer shared class cache, which is a new feature in OpenJ9. So this talk is going to be split into three parts. In the first part, I'm going to give you a high-level description of the problem and the solution discussing today. Middle part, Hang is going to talk about the implementation details, some technical information. Final part, I'm going to discuss a couple of experiments that we did in their cache so that we can evaluate the effects. So for the first part of the talk, I'm going to start by giving you some background information and context, talking about the shared class cache. Then I'm going to move on to talking about Docker, and talk about the specific parts of Docker that we're interested in this talk. And I'm going to define and describe the problem we have and the problem that we are trying to solve and the solution to that problem, which is the multi-layered shared class cache. So let's start with the SCC. So I expect that most people are already familiar with the SCC, so I'm not going to spend too much time on this. I think probably this side of the room is very familiar with it. This side of the room, hopefully, is familiar enough. So the SCC essentially stores Java classes and compiled code in a file somewhere on your disk. The idea is that we don't want to do all of the work of loading and compiling over and over. So a lot has to happen to go from a Java class file on disk to a Java class that's in memory and integrated into the rest of the program. Similarly, a lot has to happen to go from bytecode to compiled machine code. So essentially, the SCC stores the results of those processes, so we can reuse them again and again. And because the data is shared, actually multiple instances of our program can use the same data, even different programs. So that's the second major feature of the cache. So the SCC has two major benefits. First, it allows us to start faster. Second, it allows us to take up much less memory. The start faster part should be fairly obvious. We don't have to load and compile as much to a ready state much sooner. The memory footprint part is not so obvious. The key thing to remember is that the data that we load from the shared cache goes into shared memory. So if you're running just one JVM, it really doesn't make much of a difference. The difference comes when you start a second JVM, and a third JVM, and a fourth JVM. Because the data is already in memory, the second, third, fourth don't have to load the data again. They can simply access the same memory. So it's my understanding that people run thousands of Java programs on their main. So in that case, you only have one copy of the shared cache data in memory, and all 1,000 instances of the JVM can use the same data. So essentially, you use less memory. So now we're going to move on to Docker, and I'm not going to tell you everything there is to know about Docker. I'm going to stick to the parts of Docker that are relevant to our discussion. So I'm just going to tell you what you really need to know. And what you need to know about Docker are Docker images and Docker containers. Docker images are essentially like storage devices, something like a hard drive or this ancient piece of technology that I have pictured here. But there's a little bit more to it than that. It's not just like a storage device. It's actually a read-only storage device. So it's a little bit more like this other piece of ancient technology. And in that, once you create a Docker image, you can't change anything that's on that image. Similarly to once a CD is pressed, none of the data on that CD can be changed. But there's a little bit more detail. The other key point is that Docker images are layered. What that means is that if I create an image from scratch and put some data onto that image, I can give that image to you, and you can create a new image based on my image, and essentially reuse the data and add your data on top. Your data becomes a new layer in the image, and then your image just includes all of my image plus your new data. So this is a good time to mention that people really care about the size of their images. Total size of your images is very important, not only because you don't want to download a lot of data, but you also don't want to base your image on somebody's very large image. I guess the thinking is, if you only have 10 megabytes of data, you really don't want to base your image on a 500 megabyte data. So people really care about the size of their images. They don't want to download too much, and they don't want to base their image on an overly large image. So Docker containers are more or less like basically lightweight VMs. They run single programs in isolation. As far as the program is concerned, it's the only thing running on the machine, but really it's just running in a container. And finally, Docker images use images in the same way that a computer would use a CD or a hard drive. Docker containers essentially just boot from a Docker image in the same way that your computer would boot from your hard drive or from a disk that you insert into the drive or something like that. So now we're going to talk about the problem that we see try to combine the shared cache with Docker. What we want to do is create a Docker image containing a Java program. We want to include a pre-populated shared cache in that image. We want that container to start as fast as it can wherever it happens to run. We also want others who base their image on our image to be able to use the same cache and to add their data to that cache. The problem comes from the fact that Docker images, as I mentioned, are read-only. So we really can't delete anything that's already on the image, and we can't also modify any file. The deletion doesn't matter to us so much. It's the modification part that causes problems. And the way that Docker handles modification is to first copy the file that you want to modify. So it makes a second copy, and then it hands you back that copy. So in effect, you're modifying the copy. You're not modifying the original file. This scheme is called copy on write. And what it means is that when you read a file, you're reading the original file, but as soon as you try to modify that file, you get a copy made under the covers without your program really knowing it, and then you go on and modify that. So that presents a problem because it leads to a lot of data duplication. And with the shared cache, if we want others to be able to add data to that cache, they're going to incur the copy as soon as they try to add their data. So to demonstrate this problem, I came up with a fairly simple example that simulates what would happen in a real environment where you're trying to build a Docker image and use a shared class cache. So in this example, we're going to start with a base image that we're going to create. And in that base image, we're going to create a new shared cache, in this case called MySCC, and we're going to add class A to that cache. And what we end up is on the right-hand side, we end up with an image with one layer containing a single file for the SCC. Then we move on. From there, we create a new image based on the first image. And what we're doing is adding class B to the same cache. What we end up with is an image with two layers now. More importantly, we have two SCC files. And the reason is because as soon as we went to add class B to the cache, Docker silently made a copy of the original cache and then let us add class B. So the original cache that we have in our image contains class A. And the second cache contains class A. It was copied, and then we added class B to it. So I think that the problem is already fairly obvious. can take it a step further, and if we add a third image to the example, what ends up happening is we have a three-layer image containing 3 shared caches containing a whole bunch of duplicated data. So there's another problem, and that has to do with what happens when we first create the cache. So when we first create the cache, we have to specify the size of the cache file. And we have to do that without knowing necessarily who is going to base their image on ours. So you have 2 choices to make. How big do you want that cache to be? Do you want it just big enough for your data and not being concerned with anything else that happens after? Or do you want your cache to be big enough to hold your data plus have some extra space for subsequent images to add their data? And the decision comes down to adding just enough, sizing your cache just enough to fit your data, or oversizing your cache, but then having people pay the penalty of downloading your image in a large cache that's essentially empty. So that's the second problem. Now we're going to talk about the solution. So the solution here is the multi-layer shared class cache. Notice that it looks a lot like a layered Docker image in that layers in the cache are meant to correspond to the layers in the image. And as we go along, it'll become clear how that's supposed to work. So we're going to go back to our previous example, and right now it looks a lot like our previous example. We're going to add a layered approach to it. And the first thing to note with a multi-layered shared cache is that you're no longer writing to the same file. The cache is still a single logical cache, but under the covers, we implement layers using separate files. So essentially, each Docker layer is writing to a separate file. First Docker image is writing class A to the first layer of the cache. The second image writes class B to a second layer. So it first creates a second layer in the cache. That in turn creates a new file, and it adds class B to that layer. The third image does the same. And because we're no longer modifying files from the previous layer, we don't see any copy on the write. So what ends up happening in the final image is that class A is only ever stored once, class B is only ever stored once, and class C is also stored once. It's important to note now, I'll make this clear, is that we still have a single logical shared cache. So despite the fact that it's multiple files on disk, that doesn't matter to most of the JVM. As far as most of our code base is concerned, it's still a single logical cache. So second, we don't have to care about the size problem with a multi-layer cache. And the reason is because we can independently size each layer. So the first image where we create our cache, we can size layer 0 to as big as we want it, typically to the size of the data that we intend to put in there. Another image comes along and bases their image on ours. They can simply create a new layer in the cache, size it to their needs, and a third image can do the same, and you essentially have optimal behavior. So now I'm going to turn it over to Hang. Hang is going to talk about the implementation details in OpenJ9 and talk about some of the new options and things like that.
Okay, next slide, please. Okay, so here's an example of Docker layers. Younes has already talked about Docker layers in his slides, so I will go through this really quick. So Docker container is actually a read and writable layer built on top of a bunch of read-only layers. So in this example, the user is running DayTrader on OpenLiberty using OpenJ9 Java VM. We went to 1604. And the only the top layer, day trader layer, is readable and writable. All the layer below that are read only. Next slide. So when we include the shared class cache in the OpenJ9 Docker image, anything built on top of this OpenJ9 image can benefit from the shared class cache with better startup performance. So next slide. One more. So application, for example, Liberty can build its image on top of OpenJ9. So when they turn on the shared class cache, it'll load the existing data from the shared class cache in OpenJ9 layer and add Liberty classes and GCL classes loaded by OpenLiberty to the shared class cache. So next, one more. So this will trigger the Docker's copy on write mechanism. So because the existing shared class cache is in the lower read-only OpenGNet layer, so the Docker will handle any writes to a lower layer using a copy on write mechanism. So the shared class cache will be copied to the Open Liberty layer first, and then additional data will be added to the copy of the shared class cache. So next, one more. Next slide. So things get even worse when there are more layers to be built. Next. So we could have application like day traders built on top of Open Liberty, and it'll do the copy again, so it'll result in more duplicated data. So the consequences are the Docker image will have a larger disk footprint than it should be because of the duplicated data in the shared class cache. Also, it'll result in slower pulling and pushing of the Docker image because larger amount of data needs to be transferred over the net. Next slide. So the solution is a multi-layer shared class cache. So when building Open Liberty Open Liberty layer on top of OpenJ9, we write into another shared class cache in the Open Liberty layer. Rather than writing to an existing cache in the OpenJNet layer. Next. Yeah, we cannot write to a lower layer. So next. Yeah, we need to write into a new shared class cache in the Open Liberty layer. Next. So the shared class cache is actually becoming layered. So the top layer cache is built on top of all its lower layers. Next slide. Yeah, similar thing. For anything built on top of Liberty, a new shared class cache layer can be created. So in this case, it's layer 2 in the day trader layer. Next slide. One more. So which means that now JVM is able to start up multiple shared class caches, and all the top layer cache are built on top of its lower layers, and cache doesn't know about its upper layers. So we also allow cross-cache data references. So any data in the top layer cache can references all the data in the lower layer cache. So this means that self-relevant pointer doesn't work anymore because you are referring to some addressing and shared class cache. So we use a new data structure which has the cache ID and the offset in that cache to point to the unique address. So another thing is that all the lower layer caches are read-only. So so they are less likely to be corrupted. And also the JVM, the top layer cache, remember all the states of lower layer caches. So any modification to the lower layer cache will invalidate the top layer cache. So in this example, if there's any modification to layer 1 cache, layer 2 will be invalidated. Next. Yeah, the multi-layer shared class cache feature is available on OpenJ9 from release 0.17. So here's an example of how to create a multi-layer shared class cache. So you can specify a directory to cache dir command line and specify a name for your cache. So in this example, I'm using demo as the cache name. So next. You can use -x share classes list all caches to find all the caches in a cache directory. So next, so by default, the share class cache layer is 0. Next, so traditionally, if you are running on a single cache, you can simply rerun the same -x share class option. It'll start up the existing cache again, and your JVM will benefit from the share class cache in startup performance. So the single layer cache is equivalent to multi-layer shared class cache case with layer number 0. So next. Yeah, you just use the same command line option to start up the cache. Next. So if you want to create a new layer, uh, next, you can use a create layer option. It'll always ensure that a new layer is created. Next. So the data in layer 0 cache will be loaded, and the new data will be added to the new layer cache. Yes. Next. So if you run list all cache again, you will now see there are 2 caches here. One is layer 0 and one is layer 1. Next. So if you run the same command line again, it'll find all the existing cache in the cache directory. So in this case, it'll start up layer 0 and layer 1. Next. So we have a command option called destroyed all layers. So you can use this command option to destroy everything when you're done. Next. So we have introduced a bunch of new command options to work with multi-layer shared class cache. So the first one is create layer. So it'll always create a new shared class cache layer. The second one is layer equals. So you can use this command option to specify the top layer number. If the specified cache layer doesn't exist, a new layer will be created. So you can use either of these 2 command line options to create a new cache layer. The difference is that the create layer always create a new layer. So for example, if you have an existing layer 0 cache, if there are 2 JVMs launched at the same time, for example, when you're starting up Open Liberty, there are 2 JVMs started up at the same time using the same shared class command line option. If you use create layer, each JVM will create a new layer. So in this case, layer 1 and layer 2 will be created. So you can actually use layer equals 1 in this case to ensure that only one layer is created. The first JVM creates layer 1, and the second JVM sees layer 1 is already there, so it won't create a new layer. So you can use second option, layer equals, when you have multiple JVMs in a race condition to create the shared class cache. So the next one is print top layer stats. It's a command line utility option. It gives you the summary of cache statistics from the top layer only. So, for example, if you are running on an Open Liberty layer, you want to see what are the Liberty classes in the shared class cache. You can use this option to show only the classes from Liberty. Destroy all layers, so it'll destroy all shared class cache layers. Next. Yeah, so existing command line option on multi-layer shared class cache. So print stats is also a command line utility option. It'll print cache statistics from all layers. So if you run -x shared classes print stats equals ROM class, it'll show all the ROM classes from all layers. And -x shared classes will destroy the top layer cache only. So if you want to destroy all the layers, use destroy all layers option. Next. So we also add new GCL JVM TIs and DDR commands for multi-layer caches. You can use those APIs to get some information like cache size and cache layer on multi-layer shared class cache. Next. I will hand this back to Younes about JD implementation details.
Okay, thank you, Hang. So I'm just going to spend a few minutes talking about some of the implementation details that are probably going to be interested to the audience here on the JIT team. First is that most of the details of this multi-layer ishness is contained entirely in a class called TRJ9 shared cache. The rest of the code base doesn't know anything about layers necessarily. All of the internal implementation details of converting from single logical cache to multiple layers is handled in that one class. As far as the rest of the code base is concerned, it's a single logical cache, just like it was before. In the JIT, we used to have cache references that were implemented as straightforward conventional offsets. That doesn't work in a multi-layer world. So we now use what we simply refer to as virtual offsets. And this is how we allow for cross-cache references without changing all of the existing code that only ever knew about a single reference. So all of the relocation stuff and all of the related code still works with a single offset, and all the details are basically handled transparently. So a quick few words on how that is implemented. The layers are loaded into memory at various addresses. We haven't done anything to change how shared cache memory is allocated. So layers are simply allocated on demand as the JVM notices that exist, and they get allocated all over memory. But the trick is to consider them or pretend that they are laid out sequentially and are contiguous. Even though in reality they're not actually contiguous, we can just treat them as contiguous. And a virtual offset then basically maps from the first offset of the first layer and into the rest of the cache. So for example, a virtual offset of 150 in this example would be somewhere in the middle of the second layer. And that way the code base can still work with a single offset, but it doesn't have to know the details. So now we're going to move on to talking about some results. I'm going to talk about two experiments that we did using OpenLiberty and an application, in this case, DayTrader. The application isn't so relevant. And we're going to talk about the effects that we see when we go from a single layer cache, a single conventional cache, to a multi-layer cache. So in the first experiment, we had two separate runs, one using a single layer cache and using a multi-layer cache. In this case, the size of the cache was fixed, and the only thing that we did in the multi-layer case was create new layers for each new Docker layer. So we're going to talk about the single layer first, which is on the left side. And the first thing to note is that the size of our cache, in this case, is about 80 megabytes. The size of that cache on disk is about 84 megabytes. That extra 4 megabytes is essentially a combination of metadata, rounding up file system. Under the covers, this is implemented with memory map files, and you kind of have to round them up to the next page size and so on and so forth. So an 80 megabyte cache is about 84 megabytes on disk. Next, we see that in this layer, the utilization of this cache, we ended up filling it with about 36 megabytes of data. That's about 45% full. And the size of that data when we actually download it is about 15. Now, this part needs some explanation because you need to understand that Docker images are actually compressed. So when you download an image, all of the data is compressed. So an 80 megabyte or an 84 megabyte file in your Docker image doesn't mean that you download or upload 84 megabytes. It means that you download or upload much less. In this case, the 36 megabytes of actual data in the cache compresses down to about 15 megabytes. The remaining empty space is obviously trivial to compress. So that 36 megabytes of data in our cache compresses down to about 15 megabytes. And I mentioned earlier that people care about this sort of thing. They care about the size of the image, and they care about how quickly they can download it. So moving on, we add a second we build a new Docker image on top of this image that creates a new layer. And the first thing we note is that we can't change the size of the cache, even if we wanted to, because it's still a single logical cache. So in the second layer of this Docker image, it's still an 80 megabyte cache. But more importantly, it takes up an additional 84 megabytes because it gets copied as we write to it. So our first 84 megabyte cache is explicitly copied, and it takes up another 84 megabytes in the final image. That image is filled with about 20 megabytes of data, 70% full now. The thing to note here is that we started out with 36 megabytes because that 36 megabytes had to be copied from the previous layer. The cache was implicitly copied, so we started out with 36 megabytes, added a further 20 megabytes in this layer, and now we have a cache that's about 70% full. The image also contains the previous 36 megabyte cache, so that's still there. And as far, okay, that's just the copy. And as far as this image is concerned, this part of the image contributes about 26 megabytes to our download. So now we're going to move on to the multi-layer version of this experiment. Again, this is a fixed size cache experiment, so even though we can change the cache size at each layer, we're going with a fixed size just to see isolate one effect at a time. So in this image, the base image has an 80 megabyte cache. It's again 84 megabytes. It's about 44% utilized, so about 35 megs. There's some run-to-run variation, obviously. Compresses down to 15 megabytes. And then we move on to the second layer. So in the second layer, we've kept the cache at 80 megabytes, even though we have the option of changing that. A new layer is created on disk. So the thing to note is that you get a second file on disk, so another 80 megabytes. So we haven't saved any disk space thus far, but we'll see how that works out later. And the first major difference is here in that we filled this layer of the cache with about 26 megabytes, and that represents 33% utilization. And the important thing to note is that we didn't copy the initial 35 megabytes. This is a new layer. Docker didn't do anything to make a copy. And we simply filled our layer with about 26 megabytes of data. If you notice that in this example, we filled this layer with 26 megabytes, and in the previous single layer example, we filled it with about 20 megabytes. Again, that's just run-to-run variation. And finally, that 26 megabytes of data at this layer compresses down to about 11 megabytes. So here we see the actual first benefit of using a multi-layered cache. We didn't do anything to this example besides create new cache layers for each Docker image. But we see that the benefit is that we already reduced the size of the amount of data that we download, from about 40 megabytes to a little over 26 megabytes here. So that is benefit number one. That is the first experiment. So we're going to move on to a second experiment. This experiment adds a third layer to the stack of images. In this case, the base layer is an OpenJ9 image layer. I didn't mention what the layers were because it's important, but I'll mention them now. The base layer is an OpenJ9 layer. The middle layer is the Open Liberty layer, and the top layer is the actual application layer, in this case, Daytrip. And everything on the left remains the same. So besides adding a third layer to our Docker stack, all of the effects that I described before are still the same here. Nothing has changed. So we can just move on to the multi-layer case. And the first thing we've done here is actually size our layers to correspond to roughly the amount of data we expect to put in there. So our layers are now, rather than all being 80 megabytes, we take the opportunity to individually size them to something more appropriate. And we see the corresponding reduction in disk. So this is the second benefit of the multi-layer cache, is that we can actually reduce the size on disk. So in the previous example, we saw that we've reduced the amount of data we download, but in this case, we reduce the actual size of our images on disk. In this case, you can see it's a huge reduction from about 250 megabytes in single layer cache case to a little over 70-ish megabytes. So that's the second benefit. And since our cache is more appropriately sized, you can see that we filled it almost to capacity. So our utilization is high 90s, almost 100%. And here we see the same benefit that we saw earlier in that we reduced the size of download. This is the second benefit. The second benefit still holds from the first example. You can see it's actually more of a savings now. We've gone from 50 megabytes downloaded to less than half of that, almost half. But the point is that as you add layers, the benefits just increase. So in this case, we've reduced even more relative to the previous example. Yes?
So my question is, how did you decide the values for the XC, XSC, and X?
So for those on the phone.
Correspond to the utilization. My thought was that, okay, you layer, the first layer size will be 20, you set it to 16?
Okay, so the question was, how did we choose the values that we used here? How did we size the cache? And the observation was that we, I guess in the previous example, we saw 20 megabytes used, and now we've sized it to 16. So what I did was run the experiment a few times to get a sense of usually how much data is generated. In the previous example, we were actually starting with the Open Liberty layer, so we didn't have an OpenJ9 layer. It was a two-layer image. So in this, once we added the OpenJ9 layer, you run it a few times to see how much data is generated, and you size it based on that. So there's a little bit of a distinction here, but essentially what you need to do is run your application a few times to get a sense of how much data is generated at in each Docker image, and size your cache using that information.
One more thing I want to add is that there's an existing OpenJ9 issue about resize the cache. So you can start up your application with a shared class cache, which is big enough. Then you can use some new command options to shrink that cache to the size, whatever size you want.
So just to clarify, we're talking about a new option that we're adding that will eliminate this run once to see how much data you generate, and then go back and size your cache. The summary of the new option is that you size your cache to be as generous as you want, populate it, and then you can go back and basically trim it to remove the excess space, and this kind of makes life easier for people using it in Docker.
Yes. Yeah.
I've got another question.
Yeah, how are we priming the cache in each layer? So OpenJ9, OpenLib, is that here we're running to prime the appropriate classes.
So the question was, how do we populate the cache at each layer? What are we doing to get data in there? It's a good question. So I can explain this and talk about each layer individually. So the OpenJ9 layer, you basically run any application that you want, but the problem is then classes from the application are going to get into the cache, and you don't want that. So you can simply use the xshare classes boot classes only option, which essentially limits the classes that get into the cache to the set of boot classes, basically the JCL classes and J9 VM classes and things like that. So in this example, I basically ran Liberty in the OpenJ9 layer, but used the boot class only option to make sure that the classes that were in the cache in the so-called OpenJ9 layer didn't have any application classes. For the Liberty layer, I just started and stopped Open Liberty, and then for the application layer, I ran DayTrader a few times. So that concludes the second experiment. And just to finish off, I'm going to leave you first a set of references if you want further information. The OpenJ9 issue that discusses the problem, discussion of the problem that links to the various pull requests. The up-to-date OpenJ9 documentation, which lists all of the new options and how to use them. And finally, a blog post that Hang and I collaborated on that more or less describes everything I've described in this presentation. More technical detail here and there. Basically more information. And finally, some future work. We always have to end these things with future work. Some future work along these lines are things like pre-populating the current OpenJ9 Docker image. For those of you who don't know, we have an OpenJ9 Docker image on Docker Hub. And we're considering maybe populating that with a shared cache. Now that we have multi-layered caches, it makes it more attractive for users of that image they'll want to have that cache in there because it will be right-sized, it won't be too big, and they can add to that cache by creating new cache layers and adding them. So that's something we're looking into. And the second thing is to actually promote the use of multi-layer SECs in general, but multi-layer specifically in other Docker images. For example, Open Liberty community has a set of Docker images. They actually have a set of layered Docker images. So they have a kernel and a microprofile image on top and some other stuff. So they are one of the big candidates to kind of exploit this architecture. So we're working with them to kind of promote the use of multi-layered caches. Other options that other people are looking into is Jenkins and whatever other options you can think of. With that, I am at the last slide. I'd like to say thank you for listening. On behalf of Hang as well. Hang, if you'd like to say a few words, you can.
I don't have anything.
On behalf of Hang, thank you. Thank you, everybody on the phone, for listening.
Thank you.
If anybody on the phone has any questions or anybody questions in the room, I'd be happy to take. Got one question here.
I guess it's the layers are still tied directly to the class cache activity. Are there thoughts that so the lower layers, right, be able to share that common, especially if you're priming Open Liberty, right? That the default layer is going to be something generic that can be leveraged.
Yeah, so the question was that the cache essentially has one name still. Are there any thoughts about introducing separate names per layer, I guess?
Yeah, or lower layers be a common image, right?
Or have the lower layers be a common image. So that's a good question.
So I think it is possible that we can have different names for different layers, but user needs to remember which name is for which layer. So it only creates complication for the user. So I don't see a reason why we need to do that now.
Okay. Yeah, so essentially the name, it's still one logical cache. So adding multiple names.
Well, I mean, the context I was thinking of, let's say if I Absidy, for example, I have a stack, right? And I have an OpenJ9 stack that as an enterprise, I prime, right? Someone in my organization has primed my basic, let's say OpenJ9, Open Liberty, whatever frameworks I have that I'm leveraging, right? As kind of a default stack, right? But obviously I would have different applications built on top of that stack, right? Now, they all be forced to share that same name, or will somehow be, I would be able to embed saying that if I'm leveraging this base image, Open Liberty base image, there's a default class cache image baked in that I'll just be able to use, right? Independent of what my upper layer Docker images are defining.
I just want to ask if everybody on the phone heard that question, because I can't repeat it. Did you guys hear that question?
Not really.
Okay. The summary, okay, let me distill it down to like one sentence. If the cache has one name, you have to kind of communicate that name across all of the different layers. And somebody who's creating an image, has to know. I get my own echo. Okay, better. So you have to basically communicate that name, which is true. You have to, if we put a cache in the OpenJ9 image, people have to know what the name is. They have to know what directory it's in. So my thinking on that was that we could either put it in a well-known place with a well-known name. So for example, on Linux, var/var/cache is usually where caches go. So we'd put that there and document the name. But the thing that you mentioned, having different names allows people to not care so much about what name was chosen for the cache in the previous layer, and you can use your own name. So that I understand the point and why you're asking that question. So currently, one name, because it's easy. Various ways to solve that problem. Multiple names, or just document what the name is and where it is.
saying, yeah, I wasn't necessarily proposing, right? But ultimately, from a user experience, right? I'm building my application layer. I'm leveraging something underneath, and it's already defined. But it's a cache. I don't need to specify. This is my L1 layer. I'm building the L2 layer, right? Right?
That's a valid concern. That's something we may have to look into. I think once people start using it, you'll get a sense of how they use it, and then you can. This is a problem. You can do something about it if everybody's happy with the way it is, and it's not too difficult. Leave it as is, I guess.
It's not difficult, yeah.
Any more questions in the room? Yeah. Any questions on the phone? So the question here in the room was, did people ask for this feature? I have no idea. I was asked to do it. I'm presuming that people did ask for this feature.
I think it's asked by the Liberty team.
Yeah, so Liberty were the people we were involved with. Without knowing the explicit detail, it wasn't told to me explicitly, but I can kind of fill in the blanks. They have in the past shared caches in their images, and they have noticed how big they are, and they have noticed the problems of, we have to create a huge cache so that the next layer can fill it with more data and so on. So I'm guessing the problem filtered through the grapevine, and we heard about this issue, and here we are. Any questions on the phone?